Section 1.1, Functions and Function Notation. In this section, you'll learn determine whether a relation represents a function, find the value of a function, determine whether a function is one-to-one, use the vertical line test to identify functions, and graph the functions listed in the library of functions. Let's start with, what is a function? A function is a relation in which each possible input value leads to exactly one output value. Again, each possible input value leads to exactly one output value. We say the output is the function of the input. The input values make up the domain, and the output values make up the range. An example here, letter A, relation is a function. Letter B is also a function. And take a look at letter C, it is not a function. So remember, to be a function, each input leads to exactly one output. Okay, let's have some examples here. Which table, table 6, table 7, or table 8 represents a function, if any? Table 6 is a yes. How about table 7? -3, 5, 0, 1, 4, 5. So again, it is a yes. How about table 8? 1, 0, 5, 2, 5, 4. 5 has two outputs. So definitely this is not a function. Okay, function notation. The notation y equals f of x defines a function named f. This is how you read it. Y is a function of x. The letter x represents the input value, or the independent variable, and the letter y is the output, which is the dependent variable. Example here, use function notation to represent a function whose input is the name of a month and output is the number of days in a month. So let's say, for example, this month is September, so you can say f of September and there are 30 days in September. So this is your input and this is your output. Okay, another one, let's say February, and this year is not a leap year, so it has 28 days. So again, this is your input and 28 is your output. So evaluating functions, we use function notation because it is very compact, but it can also be somewhat confusing. Let's get some practice with evaluating some functions at specific inputs. So here, f of x given equals x squared plus 3x minus 4. So the x part here is the input, and this whole thing here should be your output. So letter A, we want to solve f of 2. So we plug in 2 to the x. So 2 squared plus 3 times 2 minus 4. And that is 2 squared is 4. 3 times 2 is 6. Minus 4. That is equal to 6. So we could write it as f of 2 is equal to 6. 2 is the input and the output is 6. Next one, letter B, A. So f of A, substitute A to the x. So that is A squared plus 3 times A minus 4. So that gives you A squared. 3 times A is 3A minus 4. So this is your output. Letter C, this time we want to solve f of A plus h. So we plug in A plus h squared plus 3 times A plus h minus 4. Then what is A plus h squared? That is A squared plus 2AH plus h squared plus 3 times A plus h minus 4. A squared plus 2AH plus h squared. Distribute 3. 3A plus 3h minus 4. And that is the answer. Alright, next one. Number 4, given a function h of p equals p squared plus 2p, solve h of p is equal to 3. So this time, again, h of p is equal to 3. So you substitute that to h of p here. So that is now 3 equals p squared plus 2p. And we solve for p. So first, we subtract 3 both sides, so that this is 0 equals p squared plus 2p minus 3. So we're going to solve for the input that makes the output equals 3. So that's what we want to do. So from here, this is factorable. Factors of p squared plus 2p minus 3 are p plus 3 and p minus 1 is equal to 0. You can double check this. 3 times negative 1 is negative 3. And then 3 times p is 3p. P times negative 1. 3 minus 1 is 2p. And then now you can solve this. Equate both to 0. P plus 3 is equal to 0. P minus 1 is equal to 0. So that p is equal to negative 3 and p is equal to 1. Example number 5. This time given a graph and evaluate letter A f of 2 and letter B f of x is equal to 4. So the input is 2. So f of 2. So look for 2. So this is number 2, the x-axis, and 2. The point on the graph when x is equal to 2 is this point. What is that output? What is the y value? Yes, it is equal to 1. So that is letter A. Then letter B, f of x is equal to 4. This is the output, 4. So meaning that is your y. So you have to look at your y when it is equal to 4. And on the graph, there are 2 points on the graph. And what are those? What are those x values? Erase this. The 2 x values are since f of x is equal to 4, that is x is equal to -1 and x is equal to 3. Yes. Okay. Next, one-to-one functions. A one-to-one function is a function in which each output value corresponds to exactly one input value. And the best way to tell if a function is a one-to-one function is by using a horizontal line test. If any horizontal line crosses the graph more than once, the graph is not one-to-one. So let's take a look at these examples here. Example number 6, use the horizontal line test to determine which of the following graphs are one-to-one. So you can just draw a horizontal line like this, or here, or here. As you can see that there are more than 1 point on the graph. So that fails the HLT, horizontal line test. So definitely this is not one-to-one. Okay, how about the next one, this letter B? So if you draw a horizontal line here, here, there is always 1 point on the graph. So yes, this is one-to-one. How about this one? The V-shaped graph. So if you draw a horizontal line here or here, you'll see that there is more than one. There are actually 2 points on this green line, another 2 points on this horizontal line, so meaning it's not one-to-one. It fails the HLT, the horizontal line test. Alright, next one is we have the vertical line test for functions. And vertical line test, VLT, can be used to determine whether a graph represents a function. If we can draw any vertical line that intersects a graph more than once, then the graph is not a function, because a function has only one output for each input value. Okay, so here you can draw a vertical line. You can draw a vertical line anywhere here, and you will see that there is only 1 point that is on the graph. So definitely the first one is a yes, it is a function. However, the second one, when you draw a vertical line here or here, you will see that there is more than 1 point, and actually 2 points. So it is not a function. Same thing here. So this is not a function. So next, the toolkit functions. You're going to need to remember this. So these are some parent functions. The first one, constant. Let's say, for example, this line here is y is equal to 2. That is just a horizontal when y is equal to 2. So that is a constant function, where c is a constant. Next one, identity function, or this is what you call the line f of x equal to x. And or you can write it as y equals x. Absolute value function. To remember the absolute value, remember the v value is the v shape, or you can write this is y equals absolute value of x. Next one is quadratic. meaning it's a parabola. F of x equal to x squared. So this is your parabola. And then cubic, y equals x cubed, and this is the shape. Then you have the reciprocal, 1 over x, and this is the shape. You have the asymptotes here. Then also you have the reciprocal squared, 1 over x squared, and then the square root function, or y equals square root of x, and you have the cube root function. This is the shape of cube root. So this is cubic and this is cube root. Okay, so I want you to remember all these toolkit functions. Okay, let's have some problems here. Number 27 and 29 for the following exercises. Evaluate the function of the indicated values f of -3, f of 2, f of -a, negative f of a, and f of a plus h. Let's do this. The first one, f of -3 for number 27. 2 times -3 is -6 minus 5 is -11. Next, f of 2. 2 times 2 is 4 minus 5 is -1. And then f of -a, when you substitute -a to x, is going to be -2a minus 5. And then negative fa is equal to negative 2a, negative of fa, so that is 2a minus 5, so negative 2a plus 5. And then the last one, f of a plus h, you plug in a plus h to x, so 2 times a plus h minus 5, so this is 2a plus 2h minus 5. Okay, that's number 27. 29, if you plug in -3, 2 minus -3 is 5, so that is square root of 5 plus 5. Next, f of 2, 2 minus 2 is 0, so 0 plus 5 is just 5. Then f of -a, that is square root of 2 minus -a is 2 plus a, then plus 5. And then negative f of a is just negative of this, so negative of 2 minus a. And the last one, f of a plus h, I'm gonna write it down here. So plug in that to x is square root of 2 minus a plus h, then plus 5. Next, for the following exercises, use the vertical line test to determine which graphs show relations that are functions. So remember this. So letter number 40, you can draw a vertical line test. You can use a vertical line test. So yes, this is a function using VLT. How about this? So not a function. And how about this? So whenever you draw a vertical line, there is only one point. So yes, it is a function. Then the next set of problems. For the following exercise, determine if the given graph is a one-to-one function. So meaning you have to use a horizontal line test. It's not one-to-one, there are other 2 points. Here also, look at this. You can draw that horizontal line and you see it's still 2 points, and that is again not one-to-one. And this one is a yes, it's a one-to-one. (38) Given a function f of x equal to square root of x plus 2, evaluate f of 7 and then solve for f of x equals 4. Let's do this. Evaluate f of 7. So 7 plus 2 is 9. So square root of 9 is 3. Then letter B, solve f of x equal to 4. So 4 equals square root of x plus 2. So we square both sides to get rid of the square root. So this is 4 squared is equal to x plus 2. So 16 is equal to x plus 2. And you subtract 2 both sides. So x is equal to 14. Then the last problem, 53. Given the following graph, evaluate f of 0. F of 0 is equal to 1. So here, that point is 0, 1. Then letter B, solve for f of x equal to negative 3. So the output is negative 3. So look at your y. 1, 2, 3. So the answers, the x values are when x is negative 2 and when x is positive 2. So x is equal to negative 2, x is equal to 2. You can write this as f of negative 2 is equal to negative 3, and f of 2 is also equal to negative 3. That's it for section 1.1. Yes, section 1.2, domain and range. Here you will find the domain and range of a function defined by an equation and express them using the interval notation. Okay, we're going to focus on the interval notation. We'll express many ideas such as domain, range, and intervals of increase or decrease using what's called the interval notation. While the way we write them may be new to you, the idea should be familiar. We are just expressing ranges of values on the number line. Let's get some practice by filling out the table below. X is greater than A on a number line that is from A and above, not including A. So using interval notation, using parentheses from A to positive infinity. X less than A, everything below A to the left of A, so that is from negative infinity to A. Again, close using parentheses. X greater or equal to A. This time, greater than equal, we include A to the right. So that is A to infinity. Next, x less than or equal to a, from a and below to the left. So negative infinity a. Next, between a and b, strictly between a and b, so not including a and b, so that is a, b. And then x less than or equal to a is less than or equal to x less than b, including a, not b, below b. So that is a, b. Then a less than x less than or equal to b, and a less than or equal to x less than or equal to b, meaning x is between a and b, and that include a and b. So a brackets for a and b. In general, for a function with an equation, the best way to find the domain is to actually focus on what cannot go into the function. So for us in this class, that usually boils down to doing these things. So first is you are going to look for the domains. You're going to set, the first thing, you're going to set the denominator. If you see a denominator, set it equal to 0. Because remember, we cannot divide anything by 0. Let's say 5 divided by 0 or 7 divided by 0 is undefined. Also, set what's inside. Oops, sorry. Set what's inside of an even root to greater than or equal to 0. So always remember, you cannot have an even root of negative numbers. And then when you do that, express the domain as an interval excluding any restrictions found above. And if a function doesn't have any restrictions, then the domain will be all real numbers. Or you can write it as negative infinity to positive infinity. Let's try this example. Number 1. Find the domain of f of x equals x squared minus 1. So you can see here, no denominator, no square roots. If there is no denominator, there no square root, meaning no restrictions. X squared minus 1 also, if you want to graph that, that is actually a parabola. So since there are no restrictions, so x can be any real number. So the domain is from negative infinity to positive infinity. Again, that means all real numbers. Quick check number 1. What do you think the domain is for the function f of x equal to 5 minus x plus x cubed? So like the last example, no denominators, no square roots, so meaning no restrictions. So yes, the domain is all real numbers. How about example number 2? You'll see here that there is a denominator, so meaning we have a restriction. And to do that, you have to find it by setting the denominator equals 0. Okay, so let's do that. Your denominator is 2 minus x, so 2 minus x is equal to 0. Solve for x, so we add x both sides, so that x is equal to 2. That means that the domain is all the x values except 2. So domain will be all the numbers except x is equal to 2. So now how do we write our interval notation here? That is from negative infinity to 2 union from 2 to positive infinity. This u here meaning union or. Okay. Next, quick check number 2. Find the domain of this given function f of x equal to 1 plus 4x all over 2x minus 1. There is a denominator 2x minus 1, so there will be a restriction, and set that denominator to 0. 2x minus 1 is equal to 0. Add 1 both sides, then divide by 2, so x is equal to 1/2. So the domain is our interval notation from negative infinity to 1/2 union from 1/2 to positive infinity. Example number 3. F of x equals square root of 7 minus x. Find the domain. So you have an even root here. So meaning you have to set inside of it greater than or equal to 0. Inside the root, inside the square root is 7 minus x. So take note of this. You have to set inside greater than or equal to 0. So 7, let's do that, minus x is greater than or equal to 0. So for x, if we add x both sides, that is 7 is greater or equal to x, or that means x is less than or equal to 7. What do we mean by that? On the number line, so let's say this is 7, 6, 5, 4, 3, say this is 8. X less than or equal to 7, so meaning there is a closed circle here, everything below 7. So we can write our interval that is up to the negative infinity 7. Next, interval notation and set builder notation. Again, I mentioned earlier we're going to focus on the interval notation. So the first one, from 5 to 10, you have the open circle and the closed circle here, the open parenthesis and the bracket here. 5 to 10, so 5, 10, open circles, 5, 10, 10, open circle to the left, so negative infinity to 10, not including 10, that's why you have the closed parenthesis. Then from 10 and above, there is a closed circle, so 10 to positive infinity. And to the left and to the right, that's from negative infinity to positive infinity. And we note that this is all real numbers. These are meaning all real numbers. Example number 4. Describe the intervals of values shown below and using inequality and interval notation. Inequality between 1 and 3, including 1 and 3, that is 1 less than or equal to x less than or equal to 3. The other one from 5 to infinity to the right of 5, so 5 less than x less than or to infinity. And how do we write an interval for that? Negative up from 1 to 3, union from 5 to positive infinity. Next, finding domain and range from graphs. So remember, domain refers to all the inputs. The range are all the outputs, meaning the y values. So the easiest way to find the range of the function is to graph it. So domain, since these are all the x values, you look from left to right. So that's how you write the domain. The leftmost x is, yes, -5. You can see here, that's -5. There is a closed circle here, so that's why we have to use the bracket. And here it goes to, the graph goes to -infinity, but it won't touch 5, so that is 5. And then the range, all the outputs, all the y values. So you're gonna look for the bottom part of the graph and the top part. Since this goes to infinity, so that's why this is -infinity, and the top part of this is this. The y value is 5. So remember, domain from left to right, range from bottom to top. Let's try another one. Find the domain and range of the graph to the left, this graph. So domain and range, domain from left to right. Leftmost part of the graph, the x value is -3. It's an open circle, so open parenthesis. And the rightmost part of the graph, the x value is 1. You have a closed circle, so that is the domain. Range, bottom part of this graph is this, and the y value is -4. And the top part of this graph is this, 0. Even though there is an open circle here, but there is a point here, so that's why this is a bracket. So that is the domain and range of number 6. Next, how about some domain and range of our toolkit functions? Let's say a parabola here. Domain and range. Domain, x values. This is continuous, so meaning all possible values of x. So this is all real numbers from -infinity to +infinity. The range is, this is the lowest point on the graph, and it's an upward parabola, so everything from 0 and above. How about the cubic function here? This goes up and down, so meaning it covers all the x values. This is from -infinity to +infinity. Same thing with the range. It's all going to be -infinity to +infinity. And I'll let you work on domain and range of the toolkit functions. Next, let's have some lecture questions. 3. Explain why the domain of f of x is equal to cube root of x is different from the domain of f of x equals square root of x. So what have you noticed about the 2? This is an odd root, cube root. You see the 3. And this one square root, meaning it's an even root. And remember earlier, square roots has restriction, and cube does not. Okay, so that's the difference between the two. Number 4, when describing sets of numbers using interval notation, when do you use a parenthesis and when do you use a bracket? So parenthesis, that is like when you see an open circle, meaning you do not include. And when you see a bracket, we use a closed circle or a hard circle, meaning it is included. There is a point. Okay. Next, find the domain for the following two functions. Express your answer in interval notations. Number 8, f of x equal to 3 square root of x minus 2. Square root, you see square root, meaning what's inside, set it to greater than or equal to 0 and solve for x. So if we add to both sides, x is greater than or equal to 2, and then now using interval notation, greater or equal to 2, so from 2 to infinity. Then 17, f of x equal to x minus 3 over x squared plus 9x minus 22. There is a denominator, so meaning that is a restriction, and meaning you have to set it to 0. X squared plus 9x minus 22 is equal to 0. Find the factors of this. This is factorable, so x plus 11, x minus 2, because 11 minus 2 is 9. 11 times 2 is 22. That's negative. So here, x plus 11 equals 0. X minus 2 is equal to 0. So x equals negative 11 and x equals 2. So these are the restrictions. So the domain, I'm going to write it here, from negative infinity to 11, union, since you have 2, from negative 11 to 2, another union from 2 to positive infinity. Okay. Next, write the domain and range given the graphs. So domain here, domain all the x values from left to right, that is from 2 to 8. Open circle, so parenthesis and a bracket, 8, because you have a closed circle. Range, the lowest point, bottom to top, is 6. There's a point here, and 8. And open circle, so that is close parenthesis. Next, and the last one for this section, domain and range, left to right. So everything here is from negative 4, and this continues to the right, meaning up to the infinity. And then range, the bottom part here is this. There's a point here, so that is negative 2. And again, this graph is continuous, so that is up to positive infinity. And that's it for section 1.2. Section 1.3, rates of change and behavior of graphs. In this section, you will find the average rate of change of a function, and this time you need to memorize the formula. Use a graph to determine whether where a function is increasing, decreasing, or constant, Use the graph to locate local and absolute extrema, maximums and minimums of functions. So to find the average rate of change, remember that it is the change in output and the change in input. That is the ratio. And that is what you call the average rate of change. And rate of change, that is between the average rate of change between the two input values is the total change of the function values divided by the change in the input values. Remember, from a line, a slope y2 minus y1 over x2 minus x1, the change in y over the change in x. So here you need to memorize this. Delta y over delta x, the change in y over the change in x, is equal to f of x2 minus f of x1 over x2 minus x1. Meaning the last output minus the first output all over the last input minus the first input. Okay, let's try it here. Again, you must memorize and know that formula. So it's just like thinking about solving for the slope. So given the function shown below, find the average rate of change on the interval -1, 2. So let's use that formula. Delta y over delta x is equal to -1, 2. So that's f of 2 minus f of 1 over 2 minus 1. And then what is f of 2? Based on the graph, at 2, this is the point, so the y value is 1. And f of 1 is, oh wait, sorry, it's f of -1. F of -1, this is -1 on the graph. The y value is, let me see again, oops, it's small, so sorry, this one. So that is -4, so 1 minus 4 over 2 minus 1. So that is equal to 1 minus 4 is -3, 2 minus 1 is 2 minus -1 is 2 plus 1 is also is 3. -3 over 3 is -1. So this is the average rate of change. Okay. Example number 2. After picking up a friend who lives 10 hours away, Anna records his distance from home over time. The values are shown in the table below. Find her average speed over the first 6 hours. So over the first 6 hours. So this and this. So to solve the change in y over the change in x is the output, the last output, so 282 minus the first output is 10 all over the last input is 6 minus the first input is 0. So 282 minus 10 is 272, 6 minus 0 is 6. And when you divide this, it's approximately equal to 45.33. And this is in terms of miles and hours, so that is miles per hour. So meaning this is the average speed. Okay. Number 3. compute the average rate of change of f of x equals x squared minus 1 over x on the interval 2, 4. So delta y over delta x is equal to f of 4 minus f of 2 over 4 minus 2. And what is f of 4? So let's try to get f of 4 and f of 2 here. F of 4 is 4 minus squared minus 1/4. That is 16 minus 1/4. And what is 6? We could do that later. F of 2 is 2 squared minus 1/2. So that is 4 minus 1/2. So here, f of 4 is 16 minus 1/4 minus f of 2, 4 minus 1/2, all over 4 minus 2 is 2. And 16 minus 4 is 12. Negative 4, negative negative is positive. Negative 4 plus 1/2 is 1/4 over 2. And you simplify this. 12 plus 1/4, 4 times 12 is 48 plus 1 is 49 over 4. Then all over 2. Get the reciprocal of this. 2 over 1 is going to be 49 over 8. So that is the answer, the average rate of change of f of x. Okay, and I'll let you work on quick check number 1 for practice. Okay, and then I'll show you number 4. Find the average rate of change of g of t is equal to t squared plus 3t plus 1 on the interval 0 and a. The answer will be an expression involving a. So delta y over delta x is equal to f of a minus, we're using g of a minus g of 0 over a minus 0. So g of a is, plug in a to the t, so a squared plus 3t plus 1 minus plug in 0 to t, that is 0 squared plus 3 times 0 plus 1, all over a minus 0 is a, and then here 1 minus 1 is, cancel that, and this is zeros, so this is just simply a squared plus 3t over a. Oops, sorry. Yes, this should be a squared plus 3a. There is a common factor. You can factor out a plus 3 over a. So it is equal to a plus 3. Next example. Intervals of increase and decrease. Example 5, let's identify when this function is increasing and decreasing. We always write it as an open interval of input or x values. Open interval meaning never brackets. So increasing meaning it goes up. So increasing here up to here. So that is from negative infinity to negative 2. union, and increasing here, it goes up here. That is from x values, the x value is 2 to positive infinity. And then decreasing, this is decreasing part, that is from negative 2 to positive 2. So again, never use brackets. Local maximum and minimum. A local maximum occurs wherever a function changes from increasing to decreasing. So this is the local maximum. The local maximum occurs wherever a function changes from decreasing to decreasing. Note local max is the value of the output, and it occurs when x is equal to p. Wait, there should be, this is, should be the minimum. Changing from, sorry about that, decreasing to increasing is minimum. Increasing to decreasing, that is maximum. Decreasing to increasing, that is local minimum, this point here. So it's easy to visualize it as a basketball shot. Let's see this, which has a steady increase in height until it hits its apex, that is a local maximum, and it decreases afterward. So like this one, or this. So you will have here as your local maximum, same thing here. So did you know that Steph Curry took calculus in college? I bet you know he knows about the local maximums and the minimums. Example number 6. For the function of f, whose graph is shown below, find the local extrema, that is the maxima and the minima. Here we know that this is the local maximum, and we know that this is the local minimum. So that's local minimum, that is from -1 to 2 to -2. So again, local minimum is this point, and this point the coordinates are -1, -2, and meaning our local minimum value, meaning the output is here, the output is -2. Next is the local max, where is our local maximum, is this point, and the coordinates of that point is 1, 2. So the local max value, which is the output, is, what is the output of this, is 2. Okay, example 7. Use the graph of the function f of x is equal to 2 over x plus x over 3. If you're going to graph this, So when you graph this, it's going to be like this. And this point here is the local max at negative 2.45, negative 1.63. And this is the local minimum. And this point is at 2.45 and 1.63. And then determine the intervals of the increase and decrease. So increase, that is from negative infinity, from here to here, to negative 2.45, and also from here to here, that is 2.45 to positive infinity. Then decrease, so this part here is from negative 2.45, it won't touch 0, so 0, and also decrease here, that is from 0 to 2.45. So that is number 7. And quick check number 2, I'll let you try this on your own. F of x equal to x cubed minus 2x squared minus 5x plus 20. So it's a cubic. When you try this, it should look like this. And you will see that you have the local maximum here and local minimum here. So use a calculator to find this, the coordinates here, that is the local max, and here is the local minimum. Okay. Next, again, about the toolkit's functions, intervals of increase and decrease. For constant, as you can see, this horizontal line, there is none. And how about the identity function? You can say that it is increasing. Do you agree? That is from negative infinity to positive infinity. The parabola, we have increasing is this part. That's from 0 to positive infinity, and decreasing is this part from negative infinity to 0. Here, cube root, it looks like it's just increasing from negative infinity to positive infinity. Square root from this graph, that is also just increasing from 0 to positive infinity. And then the v, absolute value, is just like quadratic function. Same thing. How about cubic function? So again, increasing from negative infinity to positive infinity. Reciprocal function, increasing, wait, this is decreasing, sorry. So decreasing from negative infinity to 0, and also here is also decreasing from 0 to positive infinity. And the last one, reciprocal, there, this is increasing and this is decreasing. So increasing from negative infinity to 0, decreasing from 0 to positive infinity. Okay. Next one. For the following exercises, find the average rate of change of each function and the interval specified. Let's recall this. That is the delta y over delta x. This is f of 5 minus f of 1 over 5 minus 1, 5 squared minus 1 squared over 4, and 25 minus 1 over 4 is equal to 25 minus 1 is 24 over 4 is equal to 6. Next, consider the graph. Estimate the intervals where the function is increasing or decreasing. So again, increasing is from here to here, that is negative infinity to negative 3, and also here increasing from 3 to positive infinity. Then decreasing is this part here, from negative 3 to positive 3. Then 23. Estimate the points at which the graph of f has local maximum or a local minimum. Local, we know that this is the local max, and this is the local minimum. So local max, that is at negative 3, 55. Local minimum, that is 3, negative 55. Just an estimate, because it is not exactly at 60. And the last problem. The graph of the function f is shown in figure 18. Based on the calculator screenshot, the point 1.333 and 5.185 is which of the following? Is it, this is 1.333 and 5.85. Is it a relative local maximum of the function? Is it the vertex? Is it the absolute maximum of the function, or a zero of the function? The answer is, that is a local max. And that's it for section 1.3. Next, section 1.4, composition of functions. Here you will create new function by composition of functions, evaluate composition functions, and then find the domain of a composite function. So we can create new functions by composing two others. It works like this. G of x, that is the output of g, is the input of f. So x is the input of g. This is g of x, the output of g. So we want to combine the two functions. We put the first function's output as a brand new input into the second function, and we use the notation on the left to express that idea. So example number 1, for functions f of x equal to x squared and g of x equal to x plus 2, we want g of x is x plus 2, that's inside, so it's like x plus 2 here. And then substitute this x plus 2 to the x of f of x, so x plus 2 squared, and x plus 2 squared, when you multiply that, is x plus 2 times x plus 2 is x squared plus 4x plus 4. Next, g of f of x. Now this is g of f of x. F of x is x squared, and you plug in x squared to the x of g of x, so x squared plus 2. Next, example number 2, the function c of s gives the number of calories burned completing s squats, and s of t gives the number of squats of a person can complete in t seconds. Interpret c of s of 25. So what do we know here? So first, inside of it, what is S of 25? This is the number of squats in 25 seconds. Okay, first we need to define S is squats. The time here is in seconds, and let's use C as the calories. So here meaning 25 seconds. Okay, but what we want is C of S of 25. So meaning that is the number of calories a person number of calories a person burns doing number of squats in 25 seconds. So that is our answer. Okay. Okay, now evaluating composite functions. Given a table, we want to evaluate f of g of 3 and g of f of 3. The first one, f of g of 3. G of 3 is 2. So that becomes f of 2, and f of 2 is 8. So this is f of g of 3 is equal to 8. So f of g of 3 is equal to 8. Okay, then g of f of 3, I'm going to write it here. First, f of 3 is 3. So g of 3 and g of 3 is 2. So we can say that g of f of 3 is equal to 2. We can also use functions with equations to evaluate compositions at specific inputs, and let's try this next problem. For f of t is equal to t squared minus t and h of x equal to 3x plus 2, evaluate f of h of 1. So first, we can solve for h of 1. Plug in 1 to the x of h of x, so 3 times 1 plus 2 is equal to 5. And then you use that, f of h of 1 is 5. So 5 squared minus 5 is equal to 25 minus 5 is equal to 20. So we can say that f of h of 1 is equal to 20. Next, quick check. Given f of t is equal to t squared minus t and h of x equal to 3x plus 2, evaluate this. H of f of 2. F of 2 is 2 squared minus 2 is 4 minus 2 is 2. And then h of 2 is 3 times 2 plus 2. So h of 2 is 6 plus 2 is equal to 8. So again, h of f of 2 is equal to 8. Letter B, h of f of negative 2. F of negative 2 is negative 2 squared minus negative 2. That is 4 plus 2 is equal to 6. And then h of that, h of 6 is 3 times 6 plus 2 is equal to 3 times 6 is 18 plus 2 is 20. So we can say that h of f of negative 2 is equal to 20. Finding the domain of a composite function. The domain of a composite function f of g of x is the set of those inputs x in the domain of g for which g of x is in the domain of f. Find the domain of f of g of x given f of x and g of x. So here you can get f of g of x. G of x is 4 over 3x minus 2. So that's like 5 over 4 over 3x minus 2 minus 1. That is now 5 all over. If I simplify this denominator here, is 3x minus 2. That's 4. When I subtract this by negative 1, negative 3x, negative 1 times negative 2 is positive 2. So that is 5 over 4 plus 2 is 6 minus 3x over 3x minus 2. Get the reciprocal of that. So I will have f of g of x is equal to 5 times 3x minus 2 all over 6 minus 3x. And now we will have restriction because of the denominator, 6 minus 3x. So what we do here is set it to 0 and then solve for x. 6 is equal to 3x, and if you divide both sides by 2, x is equal to 2. So the domain cannot be equal to 2. So that's going to be from negative infinity to 2 and from 2 to positive infinity. So that is the domain. Okay. Next, 11. Given f of x equal to 2x squared plus 1 and g of x equal to 3x minus 5, find the following. F of g of 2. So this is plug in 2 to g of x. So 3 times 2 minus 5 is 6 minus 5 is 1. And then f of 1 is 2 times 1 squared, 2 plus 1 is 3. So meaning f of g of 2 is equal to 3. Then letter B, f of g of x. This is g of x. So f of 3x minus 5. Plug in that. 3x minus 5 squared plus 1. And 3x minus 5 squared is square that. 3x squared is 9x squared. Twice of this, twice the product of this is 30x. And then square of 5 is plus 25 plus 1. So that is 2 times 9 is 18. X squared minus 60x 2 times 25 is 50, plus 1 is 51. Then C here, g of f of x, so that is g of f of x is 2x squared minus 1, and your g of x is 3 times x minus 5, 2x squared minus 1 minus 5, so that is 6x squared minus 3 minus 5. Is, oh wait, this is plus 1. 3 times 1 is 3 minus 5 is negative 2. So this is the answer for letter C. Letter D, g of x. So that is g of 3x minus 5. So 3 times 3x minus 5 minus 5. So that is 3 times 3 is 9x. 3 times negative 5 is negative 15 minus 5 is negative 20. So this is letter D. And letter E, sorry, I don't have space. F of negative 2. F of negative 2. Plug in that. Squared plus 1. 4 times 2 is 8 plus 1 is 9. So that is the answer. Last problem, number 20. Given f of x equal to 1 over x and g of x equal to x minus 3, find the following. Letter A, f of g of x. G of x is x minus 3, so f of x minus 3 is 1 over x minus 3. Then the domain of this, f of g of x. So remember, this is f of g of x is equal to 1 over x minus 3. Then letter B, this is the denominator, so you should have restrictions. That is when x, set it to 0, so that x is equal to 3. So when, meaning, what is the domain? Cannot be equal to 3, so from negative infinity to 3, and from 3 to positive infinity. If you want on a number line, here 3, 4, 5, 6, 2, 1, 0, negative 1. So meaning at 3 there is a hole at 3. That's to the right and to the left. Restriction at 3, x cannot be equal to 3. There's no point at 3. Okay? And that's it for section 1.4. Thank you.